So if everybody is okay with the Llama, then I'll let Filipe take over about how you're gonna fine-tuning your model. So Filipe, all yours.
Thanks. Thanks, Justina. Okay, so I hope you guys had fun. So Justina tried to show here how we're gonna use your Llama to serve models locally, right? This will be very useful if you're playing with open source models, and especially if you have a nice GPU machine, you'll be able to get the logics of the tokens, every inference that you do, so you can do a lot of things with Llama. It's really a very, very powerful and nice technology, right? Not a library, but there is a library too, but it's actually ecosystem. You have also the models quantized there and so on. But now I will just move to a little bit of fine tuning. So remember, like the models, the pre-trained models, okay, the way you get them directly from that store, they will do a lot of interesting things to you. You can play with prompt engineering, right? The things that I explained 2 days ago, like few shot examples. You can kind of do in-context learning, right? So train the model somehow with the prompts by themselves. You can also, try to make the model reason better by using techniques such as chain of thought, tree of thought, and so on. So you can already kind of evaluate those things that I explained 2 days ago in terms of prompt engineering. So one thing that I suggest you maybe is to get back to my slides there and maybe just try those examples that I gave, just for you to see what any model that you're downloading with Llama, it's actually responding to those prompts. But if you also recall what Gopi spoke, I think yesterday or before yesterday, about alignment in general. There are many ways to align the model, and one of these, so aligning, when you say aligning, we were talking about, somehow adjusting the model so the model gets better at what you want to do. Okay, this is alignment in general, and one very powerful way of aligning models is to fine-tune the model. And that's pretty much what we try to show today, okay, how to fine-tune a model. Now, fine-tuning, if you go and fine-tune the whole model, okay, with all the parameters, you can imagine that these super large models, you're gonna need a lot of computing resources. And one of the things that Gopi also explained, it's this technique called LoRA, okay, or low ranking adaptation, where you basically find the component, the principle, you reduce the dimensions of the matrix before you multiply them, okay? And you fine-tune the model with this smaller ranks matrix, all right? And then you project them back to the big matrix that are the same size as their original models, okay? And this is the core idea of LoRA, and that reduces a lot the need for computing resource when you are doing the fine-tuning. So what I will try to show today, okay, it's so how do you get a model from Hugging Face, okay? And then you have the transformers library where you can load these models in memory, in GPU memory, and do inference with these models. Hugging Face also has an implementation of LoRA, okay, which is compatible with their API and with their own ecosystem of models and libraries. And you're gonna use their implementation of LoRA to fine-tune a Code Llama model, okay? So I will explain to you a use case that we're gonna play together, how we're gonna obtain some data for the fine-tuning. And the core thing here today, it's really to show how you prepare the data, what are the steps that you need to follow before you get to fine-tune the whole model, okay? So with that said, I just want to make sure that everyone will be able to open the collab that I put together, okay? So this is the QR code. Just please raise your hand if you cannot access that notebook. Everyone is on that notebook? I cannot believe this. No, come on. Someone. Everyone is on the notebook? All right, that's the first time in my life. But anyways, I I just need to find the notebook here now. I think it's here, but there's another tab? Okay, yeah, I can see the tabs. But
What's going on with that?
how do I hide this?
Yeah, how to hide this?
Or maybe I can move. Let me try to move.
Oh,
Okay,
yeah,
good.
yeah,
All right.
second.
Okay, so I'm having really a hard time to believe this. So everyone is on this notebook? Is the right notebook? Wow, okay. All right, so again, I will try to show how we fine tune a model. In this case, because of the use case that we want to play around here, will be a code llama. So it's a model that is specialized into generating code. It also generates text, but it's specialized in generating code. This model is right now a bit old, I would say, but it's pretty relevant. And you are seeing here fine-tuning Code Llama GPTQ. Like, why is that? Because actually we don't have a memory enough to load the whole Llama with the full representation of the parameters. Okay, so we're going to be downloading a quantized model. So the quantized model means now you represent each floating point with less bits than what it was originally trained. Okay, and LoRA, again, it's the technique that we are going to use to kind of reduce the dimensions of the matrix before fine tuning or during fine tuning. Okay, I just want to acknowledge here that actually I got this from a lot of places. Okay, so this actually is someone else's work as well. Okay, and I just tried to put this together here in a coherent use case. Okay, but the main reference that I used to put this notebook together are here. Okay, so this Straddle Limited, I think it's a company, and I think this is a blog post where they explain how we load Code Llama quantized into a notebook. Okay, and Ragtune, I think this is another blog post where they explain how to do fine tuning with Code Llama and LoRA. And also we are going to download a data set from a paper, and the reference to the paper is there. This paper, it's I think from Google folks and from CMU and University of Pennsylvania. We'll talk about this paper, but the data set's called Pi, okay? And it's a data set that I will explain right now, and we're gonna use this data set as a use case for our demonstration here, okay? So what is this use case? So this paper where we got the data set from, it's a paper about learning performance improving code edits, okay? So the core idea is very simple. You're gonna have a piece of code like this one you're seeing here, all right? And it's slower, all right? And you're gonna use a foundation model, or in this case, a large language model, to improve the performance of this piece of code, okay? So that's why we're calling this performance improving edits, okay? So that's the use case. And these folks here in this paper, okay, the paper is Learning Performance Improving Code Edits. They provide us with a data set of these performance improving edits, okay? So they ask the human programmers to do these edits. So they give a piece of code that it's slow and say, hey, how would you optimize the performance of this piece of code? The programmer went there and provided another piece of code. So we have like pairs of slow code and fast code, okay? Or faster code as one human developer would improve the performance, okay? And these pairs are in C++, and they also have the unit tests followed by each of the. So you can, when you're evaluating, so the idea here is that we're gonna fine tune, we're gonna retrain a model to perform these performance improving code edits, okay? And the nice thing is that you can separate a piece of the data set, okay, to do evaluation later, to do a test later. And you have the unit test, so like you're gonna ask later after fine tuning, you're gonna ask the model, look, here's a piece of slow code, can you produce the fast code? And you can verify if the code that is faster or that the LLM produced actually passed the unit test, okay? So That's the nice thing about having these unit tests here. And if you find this a very nice, type of problem that you would like to push the boundaries, I just really suggest you to take a look on this paper and on this data set, because you basically have a nice benchmark to try to beat in here. Okay, so that could give you a nice research topic too. Okay, any questions about this? Seriously? Okay, it's too early in the morning. All right, so that's it. So we're gonna also pull this data. I actually downloaded this data and I put it on my Google Drive. Okay, but you can do the same. If you go on Google and you actually type in the title of this paper, you're gonna find it, and there they're gonna point you out to where this data set is in case you wanna explore more. Okay. One thing that I need to mention is like fine-tuning with this amount of data. It's very, very slow. So I don't think we're going to complete this notebook. We will not complete this notebook here today. Okay. So we'll basically walk you guys through and explain things, but you are free to kind of start running all these cells here. Okay. I managed to go over this whole notebook with one single GPU, and it took many hours, okay? So we will not complete this here today. And another thing that I need to mention, like, make sure that you have the T4 on your runtime, okay? So your runtime is actually accessing a T4 GPU. And I think you do that by coming here on runtime, change runtime type, okay? And if you just open the notebook, maybe you have CPU selected here. So make sure you select T4 GPUs, okay? These other GPUs here, they're much more powerful. If you pay the Google Colab, I'm not telling you to do that. I'm just saying that if you happen to pay, if you decided to pay, you would have access to these GPUs, which are much faster as well, okay? All right. So if you selected the T4 GPU correctly, okay, and if you run this cell here, you should be seeing something like this, okay? It's giving you some information about your GPUs, okay? The CUDA version you are using, the driver version, the GPUs, and some statistics about their working conditions at the time, and so on, okay? So you should see something like that. If you don't, just double check if you have there the T4 selected here, okay? And you can also see some CPU information with LS CPU, okay? So you tell you information about the CPU of the virtual machine that you just got on Google Cloud, okay? So now, there is this D-Bloke guy here on Hugging Face. This guy, he's amazing, and he works into quantizing all these models, okay? So, Meta just released Code Llama with the whole Llama family, and he went there, got the models, and quantized the models with many different algorithms, okay? So that's why we have selected these, all these model IDs here. This is just the bloke, like, I don't know if you guys know Hugging Face, but it's a hub of models, okay? And the bloke's just the username of the person that is providing us with these models, okay? Now you can select a lot of different models, but for this demo, we're gonna select these Code Llama 7B instruct GPTQ. So Code Llama is the name of the model, 7B is the size of the model, so it's 7 billion parameters. Instruct means it was instruct tuned, okay, version of the Code Llama, and GPTQ means that it was quantized with this algorithm here, okay? Can you select others? You can, sure. And you can go also on Hugging Face and just check the large amount of quantized models that the bloke is actually putting there, okay? And you can, most of the models that are there should work here as well, okay? Now, you have some GPU configurations in this cell here, okay? We only have one GPU, so this runtime flag is just, we're gonna use this later just to say where I'm going to allocate the tensors. And in this case will be, in this location here. And and we have some other parameters. Now we go to this part here that I want to explain with more carefully, just because this relates to some data preparation for the fine tuning. Okay. So here we are setting up the standard system prompt, and we're going to use the same system prompt when we are fine tuning and when we are making inference with the fine tuned model. Okay. So that's important that you use this system prompt when you're also doing inference with the fine-tuned model, okay? And our system prompt is very simple. It just says, you are a powerful model specializing in optimizing the performance of slow code, and then you said you must output a fast version of this slow code. This is our system prompt, all right? Remember, I think a lot of people here already spoke about what a system prompt is. But basically, every time you would do inference with the model, the system prompt goes with, concatenated with your other prompts. Here you usually do, personas and etc. You put here on the system prompt. And then you have this is model specific, but for Code Llama we have this special tags here that it's basically a separator, okay? So the instruction that you give to the model, you embrace with these tags here that you are seeing, okay? And the system prompt, you put between those tags here, all right? So we're just recording, instantiating these constants here because we're gonna use, every time we produce a prompt to Code Llama, we're gonna put our instructions between those two tags here in our system prompt between those system tags here, okay? And then I ask to print the system prompt, which is exactly what we just put in there, all right? So you need these, you're gonna probably need to, if you're working with another model, okay, you're fine-tuning another model, you're gonna have to read documentation of the model, check if these tags exist, if these tags are needed, and what are those if they exist, okay? This is very specific to Code Llama. All right, so we install libraries that we're gonna need for this notebook, okay? Go over this. Unfortunately, the internet here is a bit slow, so this will probably take some time, but you will download everything. This is just coming from pip. And this is basically, library loading and installation. And then Google Colab notebooks have some issues with locale. We just fixed these issues here. I just point you also to the Stack Overflow post where they're discussing this fix here, okay? And here I loaded the dependencies that I just downloaded there on this cell here. And then I download the quantized pre-trained model from Hugging Face and load it on memory, all right? So this is using the transformers library, okay? This is implemented by Hugging Face, and this is basically loading the tensors and the parameters of the model into memory here, okay? So again, when you run the cell, you're gonna download things, okay? And at the end, I had to stop here. I was rerunning everything yesterday, but I have to stop here. But you will see things like this, model.synth tensors being downloaded and so on. So in this case, we will be downloading almost 4 gigs here of this quantized model, okay? And then the next cell, we just print model configuration parameters. So you should see something like this, okay? The name, the path of the model on Hugging Face, the architecture, some statistics about the size of the model, the number of hidden layers, and etc. So again, you should see something very close to this if you run these cells in the notebook. So far, so good? Any question? Nope. Are you sure? Last call. All right. Okay, so after running all this, what we have is a model in the GPU memory. Now we can do inference with this model, all right? And I'm gonna show you how we do that with the next set of cells, all right? So Here, we put together a prompt. Okay, so the prompt's pretty simple. I say slow code, okay, and this I got from the paper, the Pi paper, all right? So this is pretty much the prompt that they're using there. And even if you look at the figure that I have in the notebook, that figure is from the paper, and it's the same example, okay? And it's a matrix multiplication that I just write in here. And then I finish my prompt with optimized version of the same code, and I expect completion from the model. Okay, so I don't even have an instruction say produce the code. I just leave this here, and I expect the model to produce an optimized version of the same code, of the matrix multiplication code that I just showed there as the slow code. Okay, so this is the prompt that we're going to be using to, do the fine tuning and also do the inference later. Okay. What's up? Oh, sorry. Okay, and here we put the prompt together. What's up? What's up? Oh, I really wanted to say it, to know how to make it. Okay, awesome. Thanks, Ahmed. We put the prompt together. Okay, so those instructions tags that I showed before, okay, they're here. The system prompt is here, okay, between those two system prompt tags, and we have our pre-prompt in here, okay, which is pretty much exactly this. It's coming here, and you're gonna see we're gonna put multiple sorry, we're just expecting the model here to complete with the optimized version of the code, all right? So again, this is all Hugging Face specific things, but we need to tokenize this prompt here, okay? And I just tried to look at the documentation and put here some comments to help you to understand what these parameters are, okay? So the tokenizer, we're giving the prompt that we want to tokenize, okay? Return tensors, if you say PT, that means just that you are returning these PyTorch tensors, okay? And add special tokens equals true, it will add the beginning of sentence and end of sentence token automatically when you're tokenizing the prompt, okay? And here are the tokens. Of course, you're gonna have to call another function to really see the words or the combination, the tokens with letters, instead of the tensors, okay? Oh, again, so here you're going to generate the probability distribution and decode the generated result. So, now it's when you were really seeing the what the generated result is, okay? And you can customize the decoding strategy. So you guys remember what the decoder is? I explained it on my talk about prompting, but again, I think here you were seeing like the model produce probability distributions every time you do one step of the inference, right? And then you need to decode or select the tokens based on these probability distributions, okay? And again, you can do greed, which is the simpler one. Just get the most, the token with the highest probability every time you do an inference step, okay? But you can also adopt other algorithms to kind of search for tokens based on their probability, okay? So again, lots of configuration here about the max length of the prompt, the max length of the generated results, and so on, okay? So you do the storage, CUDA, empty cache, just to make sure there is nothing in the cache, and so on. And then you, again, call this generate method of the model, okay? Again, model, you got model up there from the Hugging Face API, all right? And now you are giving the tokens as the inputs, okay? So this is, you're basically passing the prompt to the large language model in this case. These parameters here, I also got from the documentation. So just to let you know, if you do sample equals true, that means that you're gonna sample based on the probabilities instead of doing greedy sample. So if you do sample false, you're gonna be doing greedy sample. But you have another parameter called number of beans, okay? It's over here. So you remember beam search that I also showed to you guys? You have that tree where you keep some of the paths in memory while you're doing the search. You can also have the implementation of the beam search here. You just need to make number of beams larger than 1, and there is an interplay between do sample and number of beams. I recommend you to take a look on the documentation of this generate function. You're gonna understand what's in there, okay? They have an explanation on how you combine these two parameters to achieve whatever you want. Okay, max new tokens, so this is the maximum amount of number of tokens that we're gonna generate. Okay, so you will truncate if it exceeds this number of tokens. And you have temperature and top P, sorry. Also those parameters that I showed, these are the decoded parameters that I showed on my talk. So temperature, we weight the next token probabilities, okay? And top P, it's basically, okay, I wanna get only, select only the tokens whose sum of probabilities is above this threshold here, okay? So it's not that you can get a very unlikely token when you're doing top P 0.9. Okay, and then you get the generation output, which is the tokens that the model generated based on the prompt that you gave. So here you have the tensor, and then there is a structure in this object here. You're just accessing the important information that you want right now. Okay, and these are the tokens. And then you decode the tokens with this tokenizer.decode here. And you can see exactly what the model produced, okay? It gave you a not very different implementation of matrix multiplication, okay? Anyways, now what do we want to do? It's okay, I have this pre-trained model, but it doesn't seem very nice. I ask it to, improve the performance of a matrix multiplication and end up giving me the same result that I gave to the model, So it doesn't seem to be working very nicely for this task in specific. Remember, our task is improve the performance of a piece of code, all right? So what we can do to make the model better, to align the model as Gopi was explaining, for this specific task is to fine tune. We could do other things, okay? But I just want to illustrate what fine tuning is here and how you do it, all right? So let's move on to how we fine tune the model. But before that, I want to ask, any questions? You could use RAG. We could use, for example, you saw that I gave the piece of code that I want to improve the performance, and I just asked, but I could use, for example, few short examples, right? 2, 3 examples of, slow code, fast code, slow code, fast code, slow code, fast code. Now, here's the matrix multiplication. Can you improve that? Maybe this would steer the model to do something better than it did, okay? That's one way as well. Good question. Any other questions? Prem. You ran out of memory. In which cell, Prem?
In the cell where you do model.generate.
Oh, model.generate. Okay. Try to play with these numbers here.
The max prompt.
Yeah. Maybe you can try to play with them. But nice, you got there. Like I think you were close to generate something.
You can also delete your old thing.
Pardon me?
You could delete the old thing. You have the other model still.
Maybe, yes. You can clear up what you had previously. Yeah. I think if you can disconnect from the environment and reconnect, I think it will just clean up what's in there. Pardon me?
In this example, does the code actually have to run? Because results not initialized as anything.
Exactly. Like we should have let's look back on the benchmark. There we have like inputs and the test case to run this piece of code.
Okay, but
Right.
this code doesn't run, period.
Yeah. No.
Okay.
Not the way it is right now.
All right, thank you.
But there we have the instance to actually run the code. It's okay. We have time. If you need time to catch up, we can wait.
So I cannot really find this file.
Yeah, man, I think you have to. So I was checking with Jimmy what's going on. Like, we're gonna have to load the data set, and the data set I have to upload to my drive, to my Google Drive. I don't think you guys will be able to pull from there. Okay, so again, what you can do, type in the title of the paper. I think in the paper you're gonna find where the data set is, and you can upload the data set to your own drive and pull the data set from there if you want to run this. But again, in couple cells we won't be like we're gonna click to run the cell and we're gonna wait forever. Okay, very very soon. So if you just want to follow here, it's okay as well. Okay, but if you want to try by yourself, which I encourage you to do, you have to download the data, upload to your Google Drive, and then load from your Google Drive here in this notebook. Okay, so you can also make a copy of this notebook if you want to keep it, and then no one else will actually be able to see what's in here if you modify it, etc. I don't think you. I think you already have a copy. Yeah, you already have a copy. Okay? Can we move on? Or do you guys need more time? 5 minutes? Sure. Sure. All right, let's move on, okay? Okay. Okay, thanks for the patience. And so just to put everyone on the same page. So what we did so far, we downloaded the model, we prepared a prompt, okay? And we used the model to do inference, okay, with the prompts that we prepared. The prompt was, here's a slow version of matrix multiplication. Can you give me a faster version of the prompt? And what we got as a response is over here, okay? So now, I think we can align this model. I think we can make this model get better, okay, at this specific task. So what am... Okay, sorry.
I have a question from the chat.
Okay.
So is tokenizing the prompt something that is expected? Is the advantage of it performance or accuracy or response?
It is expected, and it's the way the library we are using works, okay? In terms of performance improvement, I don't know, maybe, okay? But we have to tokenize anyways at some point. We're gonna have to find the embeddings that these tokens here
Cool. Chat said thank
are
you.
mapped to, right? So yeah.
Chat said thanks.
Okay, thank you. Okay, so let's talk about data preparation for this fine tuning, okay? So again, I went to the paper. The paper will point you to a website where the data set is. I downloaded the data set, okay? And the data set, I went and uploaded the data set to my Google Drive, all right? And here I'm just loading a library where I can pull information or pull files from my Google Drive, okay? So you can do the same. Now, we're here, load the PyPerf is the name of the data set of the paper, okay? If you look there, you're gonna see that they already give you the splits for the validation, the splits for the training, and the splits for the test, okay? So here we are getting the validation and the training portions of the data set and loading here on these two variables, okay? Eval data set, train data set, okay? So here's the log. We just downloaded things from there, all right? Here we're just checking what's in the data. So this is a JSON. You're gonna see some mappings for the problem, you know, the language, some other information, the input, okay? What it's, expected, and other information about the data. Again, here you can evaluate things using the test case that they provide, so you can get things as computational accuracy or so on. And you can also use things as Rouge or Blue to kind of evaluate based on similarity, okay? And you set up some tokenization settings like left pad, so we use less memory during training. This link will take you to a Stack Overflow discussion where they're discussing this type of trick here to use less memory during the training. All right. Now we redefine this tokenized function to make the labels, the input IDs, the same. Okay. So why were you doing this? Because it's a self-supervised type of learning here. So the labels. So this model is trained like to predict the next token. Remember? That's what the model does. That's what our regressive model does. Okay? They predict the next token. So you just provide them, during training, you just provide them with text. Okay? And they read the first token, and they learn what the next token should be. So the label, okay, of the token is the token itself. And that's pretty much what we are doing here. We just assign, the label of the next token is the token itself. All right? So we get tokenizer again. I just went to the documentation and put some information here. This is all from Hugging Face documentation, just for us to understand what these parameters are doing. All right. But the core thing here is self-supervised learning means that the label are also the inputs. So we label each input with the input itself. All right. And this is what this tokenize function it's basically doing with the prompt. All right, and this will be used during training. Now we convert each data point of the data set into a prompt, so the model is fine-tuned using these prompts. Okay, so the same method that we used to generate that example that I showed previously, like this one here. Okay, these two cells here, we're gonna use again to prepare each data point for training. All right, so what we are doing here, we're just concatenating strings. All right, so the full prompt will be slow code and the data point input. Okay, optimizing version of the same code, the target, which is here. All right, so these two fields of the data set are being used to generate each data point that we're going to use during fine-tuning. All right, so this is what we give as input as each data point during fine-tuning. Okay, this whole prompt that combines the input of the data set with the target of the data set. So the input is the slow code, the target is the optimized version of the same code. Is that clear here, guys? Folks? All clear? Good. All right, and then we call tokenize, okay, with those nice, token tags that we show at the very beginning of this notebook, all right? And this will actually, So what do we do here? These tokenized training sets and tokenized validation data set, you see we're using maps. So these guys, okay, the training data, it's actually a list of a lot of data points. So we are getting each of these data points, and we're calling this function here, okay? So what we get, it's a list of the full prompts that we're gonna give to the model during fine-tuning, okay? And this will be then our data set, okay? We just prepare the data to fine-tune. How we did that? We got a raw data set from a benchmark, and we prepared the prompts that we're gonna give to the model during fine-tuning. Okay, this is the idea of this set of cells here of the notebook. Do you want? Sure, I can do it. Better? One more? Awesome. Sorry, guys. For me, it was good here, and I'm wearing my glasses, so. Okay.
So, Filipe, we got another question over here.
Question? David?
Sorry, can you explain the part where you set the results? Or sorry, you set the labels?
Sure. The labels?
Yeah, so there's this line. A line, where was that? Something where it's like lines equals input IDs. Labels equals input IDs.
Oh, yeah. So when you're doing, okay, the sky is blue. Oops, sorry, blue. So when the model is learning how to predict the next token, right? We're just saying okay, it reads this word. So what's the label for the next token is the token itself.
Right, so why don't you have to shift it by 1?
Shift by 1?
Right, so like if at like position 0, the token ID is for what you're trying to predict is the token ID of sky, so you're shifting labels by 1.
Yeah, no, this shift will be done under the hoods. Here we're just saying what the label is for this position here. So the label for this position will be the label, the token in the position by itself.
Okay.
Okay.
Confusing. Somehow, I don't know.
Yeah, no, I understand what you're saying, but this is under the hood. Okay.
Okay. Thanks.
All right. So just to clarify again, guys. So we had the raw data set, okay, and we had two, and it's a list. Okay, and we have two things there: the input and the target. the input and the target. And we have a list of this. What we did, we got these two guys from each of these element of the list, and we put on a nice prompt, and we got in a prompt, okay? And we're gonna use this prompt as a data instance during the training, okay? Each of these prompts. So we're gonna have one prompt here, another one here, okay? And these prompts are pretty much generated by this function.
Amir.
Okay, Amir, go ahead.
I was just going to clarify. I think what's going on here is you're adding a special token, so it is getting shifted over. You just have to make sure that the model you're using is only adding one special token, which I guess in this case you are, so it works. Is that clear?
You mean here?
Yeah. So there's going to be a beginning of sentence token.
That would be, yes.
So there's not a beginning of sentence tokens in the input IDs. So you're assigning the label for the beginning of sentence token to the token.
Right.
So this works in this case, but it's still like you have to keep that in mind, because if your tokenizer is adding more special tokens, like if you're adding like the chat templates, that's not going to.
Then the shift won't be correct.
Right.
Yeah. Thank you. Thanks, David. Yeah.
So we got another question over here, Filipe.
Sure. Go ahead.
Hey Felipe, maybe this is early to ask, but
No, it's okay.
this seems too low level, and isn't there a wrapper to like do all of this and like
Maybe.
maybe?
Yeah.
Okay.
If there is no, then someone could write one.
Okay.
But probably. Well, I don't know of any.
Okay.
Okay, but yeah, I know this is very low level. I totally agree with you. Totally
Okay.
agree. We probably can write a wrapper for this. Again, this is what I found. I put together, it worked, but yeah.
Yeah. Yeah, I'm just curious if there was one then.
No, totally. I
Yes.
completely agree. This is very low level. Yeah.
Yeah.
So yeah, that could be a homework here, eh? So to write a wrapper for this.
So quickly, we have another question.
Sir, Kirill.
Yeah, sorry, not a question, but more reply to that. Yes, they are wrappers. Again, keep in mind, this is just you doing your own fine tuning, but if you have a big wallet, you can pay OpenAI, and they have their fine tuning API, which you just submit your data points, and they take care of everything for you. I think same with Azure and a lot of our cloud providers. I believe there's also, Hugging Face has even a simpler API for this as well. It's just how much time you're willing to spend on this and how deep you want to go and how much customization you want and how much money you want to pay. But of course, there's different options available.
Yep. Well, the idea was let's do this very, very low cost, right? So that wasn't when we found. Any other questions?
Practical one. I'm trying to load the data and basically bonus with loading data set cached in local file system is not supported.
Yeah, I think, Jimmy, did you fix this? Can you share your solution, please? Do you have a mic there? Oh, perfect. All right. Thanks, Jimmy. Thanks, Amir. Angie.
I was the step for you, so I also noticed something. I don't know why the train data set 0, I loaded is different from yours. And the ID is different. So where we have input, it would be source code. And then where we have, I don't know, value.
Okay, so they probably updated the data.
Yeah.
Very likely.
Yeah, you could change the key.
Yeah, they updated the data.
Yeah, I fixed that part.
Perfect. So yeah, just keep that in mind. Okay, folks, the data is updated apparently. Maybe there is another schema, and you just need to. Yeah, okay, Genji, can you also please share on Slack this? I appreciate. And thanks, Kirill, for the answer. Yeah, I didn't thought about that. I mean, we were thinking about wrappers here, but yeah, for sure, there are other ways to fine-tune things. Any other question? Okay. I think Genji just found that it changed. Right, Genji? Yeah, the schema I think changed. She will share this information on Slack.
I think that is the purpose of like have this answer, because you're gonna encounter a lot of problems when you try to get your hands dirty, and then you're gonna face a lot of problems, like the data set problem, the schema problem, or whatever you wanted to fine tune your model, the format you're going to fine tune, or like the configuration there, or if you want a wrapper, whatever things you wanted to do, you will find out there was just a problem there. And the thing is that you need to try to encounter and try to fix that, or try to find out the solutions, and so that you could continue your research work on this kind of like foundational models.
Yeah, definitely, and it's nice that we're sharing
Yeah.
these pain points here, and the solutions too.
Okay, but maybe if you have the data set by your own, you have the previous schema, right? So maybe you can share the data and that's it. Because you have this data set in your in your drive, right? So that will be faster, right?
Yeah, sure. Let me see how we can do this.
Yeah, we will share that like on Slack, like after, like in break. Yeah.
Yeah. It's probably some like you need to be logged in or something, you know. Genji, how hard it is to change the notebook for adapt to the new schema? 2 words. Okay. 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 So here instead of input, it's source code, right? Can you say again?
Here, you can take this microphone.
Oh, okay. The first one is okay. And the first TGT. Okay. So this is the modification you should do to adapt to the new schema of the data. Backward incompatibility, right? So breaking changes. This is version 2.0. Oh, it's not underlined? It's just all together like this? Okay. Everyone got this, right? I would just revert here, because I still have the, you know, the old version there. All right. So I have a good and a bad news. Okay. I'll start with the bad. So we have a little bit more to cover. Okay. So we have some ground to cover here, and we're still gonna get to the exciting part. Okay. But so you know, we still need to set up some stuff, and then we're gonna get to the real training of things, okay? And then when you click on that cell, we won't finish, okay? But I have some logs here of what we get at the end, and it's actually surprising. But we have the break now. So what are we gonna do? We're gonna have a coffee for 30 minutes outside there. 20 minutes. Let's have a coffee. Let's talk to each other. And then we get back here. We set up things and finish this notebook. And then we're gonna have Ben also giving his hands-on. Good? Oh, Gustavo. Sorry, Gustavo. Oh, both. Yeah. Okay. So yeah, because it's an and, so I wasn't exactly wrong, right? Okay. So I see you guys in 20 minutes here. Thank you.
Recording stopped.
How's it going? All right. Okay, everyone is happy with coffee, right? That makes us happy.
Recording in progress.
Okay, so let's get back to this. So I just want you to thank David for calling my attention to this add special token parameter here. So this is making these add the first token, right, and then label the next one and so on, right? So thanks for that. And then, well, we went through this, and I think now we need to set up things. So one thing that we found already as an issue, sorry, Genji, you said that you also find something else with the data schema, right? And what was that? Did you share on Slack? Okay, so everyone is aware. Okay, good. There is another issue here that I want you guys to fix, and I will show what's happening. So yesterday I was running this, and this method here, this function here is deprecated. And the deprecation message asks me to change to this one. But I forgot to import this guy. So you need to import this guy here, okay? Again, this guy is deprecated. Look there. This guy is deprecated. The deprecation message tells me what the replacement function is in this one, okay? The only thing that changed is not 8, but k-bit, okay? However, you need to import the replacement function here, okay? Oh, sorry, here. And then you can comment the old one here, all right? I think changes are moving fast here, so they deprecated this function. Yep. Bit bigger? No problem. Okay. All right, guys. So yeah, here we are, importing this PEFT stands for, performance. Sorry. Parameter efficient fine-tuning. Parameter efficient fine-tuning. Sorry, too many things. Okay, so we are just importing some functions here, this object here as well. This model.train, you're just putting the model in training mode. Okay, this is again specific to Hugging Face things. And again, this should not be used anymore. You should be using this thing here. And this is basically, putting the model ready to do quantization, all right? To train over quantization. Remember that this model is already quantized. And you have some LoRA configurations. Again, I kind of look into the documentation, put some comments here for you to understand what these parameters are. So take a look on them. And we finally get the, the trained parameter efficient fine-tuned model, okay? And we're gonna move on to train this model, okay? So this guy here, be careful, because you never trained the model. You never started to train the model, okay? So I'm saving the checkpoints back on my drive, but you don't have these checkpoints there because you never actually started training the model, okay? So you only run this guy here if you actually want to resume the checking points that you already saved in your own Google Drive, okay? I think you can actually run this guy here. No, yeah, you can run. It's safe to run, okay? Because you will find if the checkpoint's in there. If it's not in there, nothing will happen, okay? But anyways, this is just resumed from the checkpoints that you were uploading there, okay? Now, if you have multiple GPUs here, you can do model parallelization, you know, and that's pretty much just configuring this. Again, we're only using one GPU, right? So we check if we have more than one. So you can run this safely. Nothing will happen in this case. But if you have multiple GPUs, this will also do, you know, model parallelization for you. Now there is a lot of training parameters configuration. I'll be honest to you, I never played with these parameters. You can, okay? The only parameter that I had to adjust was this one, and it was for memory consumption issues that I had. So again, you really need to read documentation there to check if changing any of these parameters makes sense for you, okay? But you know, it's you see here like learning rate, things like that. Pardon me? Does anyone said something? Okay. So take a look on documentation to really, if you want to play with these parameters, okay? And then you configure the trainer. Again, this is all from our API that we are using, okay? And you compile this model just to speed up training, all right? So this is basically compiling your model. Yeah, and then you finally will call, you know, the train function that will take you around an hour on an 800 GPU. This is not an 800 GPU. So when you reach this point, it's very likely that you're going to wait hours and hours, okay? So we probably want a pass through this point. But again, I think you can get here in this hands-on, okay? And once you have the model trained, remember you were saving the checking points on your Google Drive, right? So you can load them back after you train, okay? So you have your fine-tuned model. So what's happening here is that you're basically using those prompts that we prepared, remember, with the data points from the benchmark to fine-tune your model. So now, if you want to get the fine-tuned model, you just load these checkpoints with this code that is in here. Okay, so again, you're using the same thing that you use to load the quantized model. Okay, but we're actually using the PFT model from pre-trained, this function from this class. Okay, this method from this class, and you are basically loading the checkpoint from your Google Drive. So you probably need to adjust this number here if you train with more checking points. So just check that, all right? And here we just finally test what happens. So we're using the same prompt that we used previously, all right? That matrix multiplication optimization. It's the same prompt that we saw before there, okay? And we prepared the prompt, tokenize the prompt, all right? So this is the exact same code that we saw previously. And you generate, get the tokens, decode the tokens, and the response you get now from the fine-tuned model is this one. It asks you to use just, you know, numpy ... function, okay? And it actually explains So again, Code Llama also, it's trained on text, right? So it also explained, so this optimized version of the code uses the numpy dot function to perform the matrix multiplication, blah, 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 blah. But you see, it didn't repeat the matrix multiplication that you asked it to improve, but now it's giving you a function that it's actually calling another function. So the import is actually, missing from there. This code won't run, right? So you have tags, you'd have to clean up this code and import the numpy function such that it will actually run, But the reality is this is faster than the original code, okay? This is what I want to show you guys. So again, I think the real value of this notebook, it's, maybe you can share this with your students, or if you are a student and you need to do some fine tuning, I think this notebook will be very useful for you, okay? So sometimes reviewer will ask you, why don't you compare this method, very nice method that we proposed with fine tuning? Okay, you have this, something on this sleeve, right? So, and to illustrate also what you need to do to do this fine tuning. You have some data preparation, you probably need, like depending on the downstream task that you are working on, you're gonna have to find data to fine tune and so on. So these aspects that I also want to illustrate to you here. And yeah, I hope you have learned something. And now I will hand over to Ben and Gustavo that will talk about DSPy, okay? DSPy, remember DSPy, the prompt compiler that I mentioned during my talk? So these guys will also give you an example of how to use it. Thank you very much, and I'll be around. Thank you.
So Filipe, just before you turn that off, over here, we actually have a question.
Okay, we have a question, awesome.
Thanks again, Filipe.
Thank you.
I'm like kind of wondering if we can use these checkpoints to draw that nice graph to show on stage, on more and more fine tuning, our performance comes down, and
Definitely.
I mean our accuracy goes up.
Yes, you can see. Yes, you can definitely see it on the validation data how things are. Yes.
And that's a way to figure out if you need more training or less training, or if you need
totally. Yeah. Well, if you still have data, you can keep training.
Okay.
Right?
And if you don't, that's kind of okay.
Okay.
And
Thank
then
you. That's
somewhat
a great
related,
question.
somewhat related to that, where do we set up the checkpoints? Because that path is never mentioned in the setup. Is it all automatic?
No, I have a prefix for the paths here. But
No, that's when loading it, right?
Oh, okay, yes. I'm saving it.
That's also loading?
No, it's below this.
Below.
When you're training, you have the training arguments. So during this, you set up the output directory.
Yeah, here.
But output there is not the same as PyPerf.
Pardon me?
The output there is PyPerf. You set that up earlier. It's a different directory. It's not that subdirectory where you load the checkpoints.
I think it prepends those numbers automatically here.
The numbers and also the
yeah.
name. Okay.
Yeah. No problem.